Welcome back. In this video, we're going to talk about the derivation for the equation of a tangent plane to a surface given in implicit form. We'll talk more about why we want to do it in implicit form. The short answer is this is the mother of all equations. Any equation in explicit form can be written as an equation in implicit form, which we'll see in a future video. This video is really about constructing a general equation for a plane tangent to the surface, f of x, y, z equals 0, at a particular point, p naught of a, b, c on the surface. Let's do a quick recall of equation for planes. So when we look at a plane, so this is This is a recollection of how we constructed planes. So let's say that we have a plane in R3. So this is some plane that we want to graph. And recall that we had kind of two equivalent ways to think about this plane. If we slap a point P naught, in this video we're going to call P naught A, B, C. And I want to be really careful. In previous videos, we've let A, B, and C be the normal vector. It is no longer generally the components of the normal vector are not A, B, and C. That's the specific point. And we said that one way to construct the plane was to construct the set of all points, which we would call the general x, y, z, such that this vector right here, the vector that connects the specific point to any point on the plane, is directly orthogonal to what we called a normal vector. I do want to emphasize right now that this was one method of constructing a plane, but we also said that as long as you had two different directions on your plane, maybe one of them you called x and one of them you called y, then the set of all linear combinations, so if I take some scalar times x and some scalar times y, that would give me the entire plane. And then we said that the normal vector would be the cross product of those two vectors. And the reason this is important is if I have two vectors or any set of vectors that lie in the same plane, the unique normal vector is the one that defines that plane. And those are equivalent, right? As long as I have different vectors that lie in the same plane, I can get a normal. Or if I have a normal, I can create, using this point, vectors that lie in that plane. And we're going to use this fact later on in this video. Back to the work at hand. We just reminded ourselves that in order to construct a plane, we need a point on the plane and a normal vector to the plane. So that's going to be the entire method or mechanism in this video, is to figure out for a surface, f of x, y, z equals 0, how do you get a point on the surface? Easy problem. How do you get a normal vector to the plane? Much more interesting problem. Let's begin with a search for the normal vector. In order to get the point, all we need to do on a plane, all we need to do is find values a, b, and c that satisfy this equation. And you could literally set one of these or even two of them to 0 to find the missing parameters. To find the normal vector, we have to do something much more clever. And in particular, what we're going to do is assume that we can graph the surface, and then on the surface we can graph any curve, parametrized curve, that actually sticks on the surface. Remember that one of the really cool ways to define curves in R3 was to use parametric equations or vector valued equations, where we have a single variable input and in this case a 3-component output. This would look something like so this is the idea here. We've got some surface. For some reason, all of my surface looks like elliptical paraboloids, and that's because the other ones are hard to draw. All right, so here we've got some surface. We slap some point on this surface. So this would be the point P naught A, B, C. And of course, this would mean that f of A, B, C is equal to 0. And then the whole idea in this situation is we're going to pick any curve through this point. So for example, we could pick this curve C. So we'll call this curve C1. We could also pick a different curve that comes from a different direction. So maybe we pick the curve that comes down from this direction, right? So this would be curve C2. And in fact, in this video, the whole idea is that it doesn't matter what curve I pick. The only thing that matters is that the curve is guaranteed to go through the point. So in general, when you look at the equation for any curve, the curve should be written as a set of 3 components, x of t, y of t, z of t. And then moreover, we're going to restrict those components to the surface itself. So because the curve C is forced to lie on the surface, each point in C must satisfy the surface, which implies that if I were to actually evaluate f at the individual components on the curve, well, every single point on the curve is on the surface, which means that each of the t values, when you substitute them into the vector and you put that vector into the function, it should satisfy the equation of the surface. Well, the equation of the surface was f of x, y, z for any point x, y, z on the surface must be equal to 0. Right? So another way to say this is when I look at the curve and I evaluate f at the output values of the curve, this is equal to 0. Do you notice something here? What type of function, when we write it like this, what type of function is this? And I'll give you a major hint. Chain rule. So this is x, y, z. Each of these has a single variable input. Yeah. This is a composite function with 3 intermediate variables and 1 independent variable. And we say that the derivative of this thing, which we're going to talk about in a second, would be the product of the derivatives of the individual branches. So this is partial f partial y dy dt, and that's an ordinary derivative. Here's a partial derivative with respect to z, and then this is an ordinary derivative with respect to t. And the reason that this is super useful is if we wanted to find derivatives of this particular function, remember this function right here would actually be this curve, which is quite amazing, right? This curve is in R3. This evaluates as 0 because it's on the surface. So if we wanted to find the slope of the tangent line or the direction of the tangent line, we could say to ourselves, well, let's go ahead and take the ordinary derivative of this thing f of x of t, y of t, z of t. Well, we know via the chain rule, let's just go ahead and remind ourselves, when we take this derivative at a point t, we're going to go ahead and take the partial derivative of f with respect to x times the ordinary derivative of x with respect to t, and we'll add that to the partial derivative of f with respect to y times the ordinary derivative of y with respect to t. And then finally, we'll take the partial derivative of the surface equation with respect to z, and we'll take the ordinary derivative of z with respect to t, and then we'll add all those products. Do you see a dot product? This gets into what we saw in lesson 11. Here, each of these things is actually a component of a corresponding vector. So this is partial f x, partial f partial y, partial f partial z. There's a vector. And then this is now multiplied by the derivative of x with respect to z, t in the first component, derivative of y with respect to t, and then the derivative of z with respect to t in the second component. And then this thing now, we look at this as f sub x of x, y, z for any point x, y, z, f sub y of x, y, z, f sub z of x, y, z. And then we're going to dot that with x prime of t, y prime of t, z prime of t. Well, do you recognize this vector right here? I like when you look at this vector right here. What's that vector right there? Yeah, that vector is the gradient of the function that defines the surface evaluated at any point x, y, z. And then do you recognize, this is a dot product, of course, because it's a product between vectors. Do you recognize this from the last video in this thing? Yeah, this is the direction of the tangent line to the curve that's on the surface. Okay? Well, what does this allow us to say? This means that if we want to find the normal vector to the plane, well, we don't know anything about the normal vector to the plane, but we do know that the gradient dotted with the tangent direction gives you this thing. But remember that the entire equation here, when we had f of x of t, y of t, z of t, this equation was equal to 0, right? Because remember, the curve itself lied on the plane, so it must satisfy the equation of the plane, which means when we take the derivative of the left-hand side, it's got to equal to the derivative of the right-hand side. But what's the derivative of 0? Of course, it's 0. This is pretty amazing. This is the three-dimensional generalization of the two-dimensional observation that the gradient is orthogonal to the level curves, or the tangent line to level curves. This says that the gradient of a three-dimensional function is orthogonal to the tangent lines of level surfaces. And that's any tangent line. And the reason that this is quite remarkable is we just showed that the tangent vector, the direction of the tangent vector to any curve, it didn't matter which curve that we chose, no matter what curve we choose, as long as that curve goes through a particular point, and we take the vector in the direction of the gradient at that point, that the gradient will be directly orthogonal. So here, remember that if you wanted to take this vector, the tangent direction here, we call this r prime of t, and that was from the last video in this sequence. And this thing would be r prime at the actual point p naught. And then here, the vector directly orthogonal to this sucker is going to be the gradient at that. And we just saw that the gradient dotted with the direction vector of the tangent line there, that dot product is going to be 0. Well, what do we say about dot products that are 0? We say that the angle between them is 90 degrees. This is where things get really cool. We said that this was true for any curve. So in particular, if we take two curves that have different tangent directions, so maybe this tangent direction we'll call R1 prime because it's on curve 1. And then maybe this tangent direction, you're going to have to forgive me, we'll call this tangent direction R2 prime of t. So you have two different directions, and yet no matter what direction we choose, the gradient vector at that point will be orthogonal to both of them. Isn't this amazing? So this is orthogonal to this one, and it's orthogonal to this one. I don't know if you noticed this, but these two vectors are going to lie in the same plane. And in fact, if you take a third curve, so let's go ahead and take this curve here, this vector right there will also lie in the same plane, and yet the gradient will be orthogonal to this vector. Same thing over here. This vector on a different curve, perhaps, is going to be in the same plane as all these other tangent vectors. The gradient is orthogonal. So you have a bunch of tangent vectors lying in the same plane, and then you have a single orthogonal vector to the plane that contains all of these tangent vectors. Well, what would we say about this vector? This vector must be orthogonal to the plane that contains all of these things, right? So what that means is that the vector which is given by the gradient dotted with any single one of these things is 0, which implies that the normal vector to our tangent plane is given by the gradient of the actual function evaluated at that point, which implies we have just finished the two things that we needed. We needed a point on the plane, and we needed a normal vector to the surface that defined the normal vector of the plane. So the point is given by whatever the coordinates are, and the normal vector is given by the gradient of the function that defines the surface evaluated at the particular point. Pretty cool, right? So what we say is the tangent vector for any curve along the surface through the point P naught ABC must lie in a single plane, the plane that the tangent vectors lie on. So if you take the R prime of any curve, they all lie in a plane. This is the tangent plane. Moreover, the gradient vector evaluated at the specific point is called the normal vector to the plane. And this is exactly what we wanted to confirm. We now have exactly what we needed, which is a point on the plane given by P naught of A, B, C. And we have the normal vector to the plane, which is the gradient at the input value A, B, C. And then we wanted to create the general equation for a plane. Well, we knew that the general equation for the plane was going to be the normal vector dotted with the vector that connects our specific point to any general point. And then this dot product, because the normal vector was going to be orthogonal to any vector on the plane, this dot product would be 0. Well, we've just said that the normal vector is the gradient of the surface equation evaluated at the particular point. And then here we knew that this was going to be the general point P minus A, the general point Y minus B, the general coordinate, and then this was Z minus C, and this must be 0. And what I wanted to say was N is the normal vector, P naught is a specific point on the plane, and P is a general point on the plane, which means that the vector connecting P naught to P is any vector on the plane, and that vector must be orthogonal. If you need a reminder on this, go back to lesson 5, I suppose, where we derive the general equation for a plane. This normal vector was super special because it was actually given by the partial derivatives in each of the directions. So this is f sub x of ABC, f sub y of ABC, and f sub z of ABC. And then this was x minus a, y minus b, z minus c. And we said this was equal to 0. Well, this now gives us a way to construct the general equation for a tangent plane. So then this is f sub x of ABC multiplied by x minus a plus f sub y of ABC, so the partial derivative with respect to y, multiplied by y minus b, and then finally we have f sub z of ABC multiplied by z minus c, and the whole thing is equal to 0. Guess what this is? For any surface that's defined implicitly, this is the equation of the tangent plane through the point ABC to the surface. In the next video, we'll take a look at how to use this equation to actually find the general equation or general expression for a tangent plane through a point. See you there.